Speaker of the morning is Johanna Mathieu from the University of Michigan.
Mic on? Can you hear me?
Yeah.
The mic's on? Okay. Great. Well, thank you so much for inviting me to be a part of this workshop. I very much appreciate it. So my talk is about optimal power flow with stochastic reserves, and I'll break down that title to tell you exactly what I mean later. I'm an assistant professor in electrical engineering and computer science. My training was in control systems, but I've moved very much into the power system community at this point and consider myself a power engineer. And you can judge based on the content of the talk which category I fit in based on Janus's descriptions. This is joint work with a number of collaborators. So Bowen Lee was my PhD student. He just graduated. He's doing a postdoc now at Georgia Tech. Maria Racapolo is a professor now at the University of Melbourne in Australia. Ruwei Zhang, Yiling Zhang, and Xichen Shen are at the University of Michigan. And for this specific work, I collaborated a lot with people from operations research who are experts in stochastic optimization and chance constraint optimization. Okay, so this is the outline for my talk. So first I'll explain to you what I mean by stochastic reserves, because it's not a very common term. And then I will talk about how we're defining chance constraint optimal power flow problems that incorporate stochastic reserves. I'm going to show you how we then solve that problem using a variety of conventional solution approaches, and then how we explored the idea of using distributionally robust optimization, which seems like quite a hot topic right now in operations research, and how we found that it might not be the best solution technique for this sort of problem because it's too conservative. And so we've developed a lot of different methods to try to make it less conservative and achieve a more cost-effective solution for solving the optimal power flow problem. And then I'll give you some concluding remarks. So in my work in general, you can sort of hear from what I'm already saying, we try a lot of different methods to see what works and what doesn't work. And I'm not necessarily pushing this as like the right way to solve this problem, but more of an exploration of if we do use these methods, what do we learn? And how can that help us solve problems in the real world? So some of these techniques I don't think system operators would ever use. Just like the conversation with Shmuel's talk earlier, this is another version of a stochastic optimal power flow problem. It's unlikely that they would get implemented just like this, but I think the results give us insights that can help us reformulate the problem in a simpler way that can achieve results that are close to the optimal solution. So the first part, what are stochastic reserves? So stepping back, reserves are needed to balance power systems because in general we are doing forward planning where we're forecasting things like wind, solar, load, etc. And then we're dispatching the power system to ensure supply and demand are balanced. But because we're using forecasts in real time, the system might not be perfectly balanced. So we save some generation capacity to be able to ramp up and down to match forecast error. And you probably have seen these types of plots before, but these are plots showing renewable energy production. This is solar production over the course of one day for a solar farm in Arizona. And you can see every time a cloud goes by, there's this huge dip in production, and that's actually somewhat hard to forecast when these dips are going to happen. This is a wind power production curve from BPA in the Pacific Northwest in the US over the course of an entire month. And you can see in general, throughout a day, there's a lot of variability. And then there might be whole periods of time where there's no wind in the system at all. So with more intermittent renewable energy generation, there's been a number of studies that have shown that we need more balancing reserves in our systems. And those reserves could come from generation like natural gas power plants or hydro power plants, but they could also come from new resources like distributed energy resources, and that's going to be the focus of my talk, using distributed energy resources to provide balancing support. And the type of balancing reserves I'm talking about are able to balance out forecast error on timescales of seconds to hours, where when I mean hours, I mean 1 to 2 hours, not much longer than that. So this problem here, where the wind totally goes away, is not going to be solved by balancing reserves. But this problem here should be. So the resources I'm talking about are able to shift consumption, production, et cetera, on short timescales to help balance the system. Okay. So like I mentioned, the types of resources I'll be talking about are flexible loads, also distributed energy storage, so small scale storage that might exist in the system. So these could be Tesla Powerwalls, electric vehicles, so batteries. Also flexible loads could be things like thermostatically controlled loads, air conditioners, refrigerators, water heaters, anything that has some flexibility in terms of when it operates. So if you have a thousand of these devices that all consume small amounts of power, they could collectively track a balancing signal, while at the same time ensuring that the total energy consumption is unchanged versus their baseline consumption. So I'm talking about shifting loads in time, not decreasing loads like a traditional demand response type program, so it's only shifting. So just to show that if you're controlling loads, and normally they would consume this much power over time, I might send them a balancing signal that looks like this, so that they should increase consumption when there's a lot of renewables on the system or decrease when there's less. And then they try to follow that as best they can. So that's the control problem. And I've done a lot of work on this problem in the past, mostly from a controls perspective. I told you my background was more in controls, although in this talk I'm going to mostly talk about optimization. And what we've been trying to do is understand if you have an aggregation of these loads, how you can control them in an effective way to track a balancing signal, while at the same time not requiring advanced communication systems to send high-speed bidirectional information to the loads, okay, because putting those systems, those communication and sensing systems in place would be costly. And so we've developed a variety of methods to do state estimation to understand how they're behaving, and then control design based on the estimated results, and then send broadcast control signals. So we're measuring things in the network, in the distribution network, to infer what the loads are doing, and then close the loop in a feedback control system. So I have a bunch of work on this, and I'm not going to go through the details of what we've done here, but we've looked at a variety of different realistic cases where there's communication delays, where there's different level of connectivity, where there's different frequencies of information available. And now we just got a big grant. We're going to be testing some of these ideas in practice, and so hopefully they'll work. And then we can demonstrate to the utility companies and the load aggregators that it works sufficiently well that they should be doing this more. There's a lot of work in the US where people are working on these types of problems, and also in many other countries as well. I've listed just a small number of the papers that try to solve this problem in a variety of different ways. But basically it's coordinating resources, distributed energy resources across the network to provide balancing. So we can model these types of resources as if they're storage. So obviously we can model batteries as storage, but we can also model most loads as if they're storage as well. So if you take an aggregation of loads and you look at how much power they consume over the course of the day, if you make them consume more than their nominal amount of power, their baseline power, then they could be considered charging. And if they consume less, then they're discharging back to the system. So it's just like a generator, but your base point's different. It's not zero anymore. It's based on the baseline consumption of the loads. This is not new. People have been working on these storage type models for a while. And instead of just doing simple things like this, you could also do more advanced things like this, where they track these types of balancing signals. And you can write the dynamics of the system very simply, where S is like the state of charge of a battery that evolves over time based on the deviation of the load from the baseline. And the power consumption of the loads at any time is bounded, so there's some maximum with which you can increase the load, and there's also some minimum which you can decrease the load based on the constraints of the loads themselves. For the type of work we're doing here, we're assuming that the loads are controlled in a non-disruptive way, so I'm not manipulating loads in a very drastic way where consumers would notice what's going on. But for instance, if you had an air conditioner that was participating in a load control program to provide balancing, the strategies that we've used have assumed that we can switch air conditioners on and off, but that the temperature in the household doesn't deviate from the nominal range, because usually there's some set point that you set, but the temperature is allowed to be in a range plus or minus that set point temperature. The temperature is not controlled incredibly precisely, but is allowed to be maybe in a 2-degree range. And we're not changing the range. We're just changing when the device is switching on and off, and that is allowing us to aggregate the resource and provide balancing support. So there's some, based on how many air conditioners in that case are on the system and available to participate, and based on the temperatures in the houses, there's some number that you can switch on or off at any time. And that's basically enforces the power capacity. But there's also a energy capacity, how much you can shift the load over time. So you can't just arbitrarily shift all of the air conditioning load to the nighttime, of course, because the houses will become too hot. So there's some embedded energy in the system that allows you to shift the system from sort of one side to the other. So that's the energy constraint. So this is kind of like the simplest model you could come up with for aggregations of loads as storage. And that's based on some prior work we did years ago. There's a lot of people who have looked at this and come up with different types of models that boil down to the same basic idea, where you have power and energy constraints, and you have some kind of dynamic relation of how the energy in the battery evolves over time. And here's a sample of those, but there's again many others, and some of them become more precise or less precise at representing the aggregation. And how well you can do in part depends on how many details you put in. It also depends on what type of loads or storage you're modeling, because lots of loads have more complex constraints that would be hard to capture in this kind of aggregate system model. So these types of storage models are very imperfect. They give us a sense for the flexible capacity of the resources, but they're generally not great. In fact, a lot of them are too optimistic, and they'll tell you you have flexible resource when you don't, and that's not very good for planning problems. Another important thing is that the capacities, the energy and power capacities, aren't perfectly known. To know that, you would have to have, well, generally they're not perfectly known because a load aggregator wouldn't have perfect information about all the resources, their dynamics, the local conditions, and the consumer's flexibility, right? So generally they're dealing with some uncertainty about what their population even looks like. And also the capacities can vary over time. So in the plot I showed you before, I showed that the power capacity was varying over the course of the day. In the middle of the day, there's lots of air conditioners connected to the network, so there's more capacity. At night, maybe people switch off their air conditioners, there's less capacity. But these capacities are varying as a function of stochastic processes like temperature, humidity, et cetera, for air conditioners, or driving patterns for electric vehicles. So there's lots of uncertainty in this problem. So these models are inherently uncertain and not very good. And in addition to that, in addition to the models of the capacity not being very good, the control responses that you get from the loads might have errors too. You send a control input, you don't get what you want. Fortunately, we close the loop and solve feedback control problems, so you can kind of often correct that, but there's some uncertainty in the response. So in this talk, I'm not going to focus on that last point. I'm going to focus on planning problems where we're trying to schedule capacities of resources to provide services. And so I'm going to consider storage models which have uncertainty because of any of these things. The models are imperfect, the capacities aren't known, and they're varying over time in a stochastic way. So as a concrete example, this is a case where you have 1,000 electric space heaters that you're aggregating together, and you're controlling them in such a way that you're switching them on and off to track a balance, so that their aggregate power consumption tracks a balancing signal. And what we did was we computed the total energy capacity of the aggregation and the power capacity as a function of the outdoor temperature, which is in degrees Celsius in this plot. And you can see when it's very, very cold, there's more electric space heaters that are connected to the system, providing space heating to the consumers. So the capacity is quite high. As it becomes warmer, people shut them off. Some people, but everyone has a different preference for when they shut them off. So as the temperature becomes warmer and warmer, there's fewer electric space heaters available, and so the capacity decreases. So that's how you interpret this plot. Actually, if you go even colder and colder, this line starts coming down because the space heaters have to run full out to heat the space, and they're no longer able to keep up with the needs of the consumer, so they also become no longer flexible and able to be controlled. So for very cold temperatures, you also wouldn't have flexibility. There's just this sort of like sweet spot here where there's some flexibility in terms of their switching. The power capacity plot looks similar in terms of the maximum power capacity. This is how much we can switch on or off at any time. And the power baseline is how much energy they'll consume as a function of temperature. Okay. So basically, if you're at 5 degrees C, you can increase the load by this much or decrease the load by this much. And then if you hold that load increase or decrease over time, the energy capacity becomes the constraint that you have to monitor to figure out how long you can hold that change. So in planning problems, which I'll talk about, so day-ahead planning problems, not long-term planning problems, but day-ahead planning problems, we have uncertainty in this dimension because we don't know the temperature next day, the outdoor temperature next day, when we might be doing this type of planning precisely. So we don't know exactly where we are in the temperature space. So if we estimate that it's going to be 15 and then it's actually 18, you could have a huge decrease in the population in this case. This is all based on simulation models, so the actual curves will also be much more interesting and complex than these. But in reality, you also have uncertainty in this dimension because at any given temperature, you might have a forecast for how people will behave based on the temperature, but they also might choose not to turn on their space heater that day because they're going to build a fire instead, or they're on vacation, and there are lots of different effects, right? So you don't actually know if this dimension is accurately represented either. And also, in addition, if they've been participating in load control programs in the past and they've been doing different things to their system and they want to opt out, then maybe that resource won't be available either. So there's lots of reasons why there's uncertainty in both dimensions. I'm going to mostly in this talk focus on this uncertainty. I'm going to assume we have a model of the temperature, the capacities as a function of temperature, and look at if we get the temperature wrong, how wrong can we be in terms of the scheduling problems. So I'm calling these sorts of things stochastic reserves. They're providing balancing reserves, but we don't know their capacities precisely. And that sometimes terrifies people I talk to in the industry, because reserves should be reliable. That's the point of reserves. They're there when you need them. But these reserves are not reliable. And so essentially, what you need to do is back up some of the unreliable reserves with more reliable reserves. But that can still be a cost-effective solution for the system if these unreliable reserves are really cheap. So if you can access these flexible load capacities very cheaply, and the total reserve for the system will probably go up, but you'll need less expensive generator reserves. So that's why it's sort of interesting to think about this. But there's different ways to handle this. How do you handle this? Well, you can assume that the uncertainty should be managed by the load aggregator. So the load aggregator computes what it thinks is its capacities, and then it offers to the power system operator what it thinks it can provide to the system. So they might be a little bit conservative in their offer, depending on the sort of the penalties associated with not delivering. So if they're a little bit conservative, they don't offer everything because they're not sure that they can provide it in real time. So then you're asking the aggregator to deal with the uncertainty. You could also ask the system operator to deal with the uncertainty. So in that case, the aggregator just says, this is what I know about my resource, and I have some uncertainty about it. And then the system operator incorporates the uncertainty in the optimal power flow problem. And in that way, you can do better, because you can figure out, but basically everybody's uncertainty will be aggregated together when you solve the problem, and you'll get some nice averaging so you can handle more uncertainty. Or you could take some sort of hybrid approach. So what we do in this case is assume the system operator has to handle the uncertainty. So the system operator is going to optimize the system subject to some information about the uncertainty of the load aggregation. I'm not saying that this is realistic. Again, this is probably terrifying to the independent system operators in the US or the TSO operators here, because they don't necessarily want to deal with these uncertainty models of every resource in the system and include that in their planning problem. But by solving this problem, we get a sense for how well we could do. And then we could design strategies to try to get as close to that optimal as we can. So next I'll talk about chance-constrained optimal power flow incorporating these types of resources. First I'll talk about chance-constrained optimal power flow where I don't add these pieces. So there's many different approaches to incorporate or to formulate optimal power flow problems using chance constraints. I'll talk about what I mean by chance constraints in a second if you haven't seen it before. Basically, it's uncertain constraints hold with a certain probability. Excuse me. So in this case study I'll show you in the next slide, we're going to assume that there's no stochastic reserves in the system, but there is wind power uncertainty. And we'll assume that we have 2 wind farms. We're using the DC power flow equations. It's still an open question for how to embed the AC power flow equations in the chance-constrained optimal power flow formulation. So we're taking the easy way out in this case because we're focused on answering this question about stochastic reserves. And we're assuming that generators use an affine control policy to deal with wind forecast error, meaning that we schedule their outputs, the generator outputs, and then they adjust in real time to the wind forecast error based on based on a participation factor. So participation factors are already used for automatic generation control type strategies. It's how much the generator responds based on a signal sent from the system operator. So in this case, you take the total wind forecast error and you allocate that to all the different resources, generators, providing reserves in the system in a way determined based on this D. So every generator will have a reserve action, R, that's a function of their participation factor and then the total amount of wind forecast error in the system. And if you sum all the D's together, you'll get 1 to fully compensate the total wind forecast error. So we're assuming this affine control policy. It means that our solution isn't as optimal as if we had optimized over the structure of the control policy itself, but this allows us to formulate something tractable. So in this base problem, the decision variables are the generator power outputs, their reserve capacities, and the participation factors D. And then this is the formulation for this it's become a somewhat standard chance constraint optimal power flow formulation. It's very similar to the one that was proposed 5 years back, sort of in parallel by these two groups at ETH and at Los Alamos and Columbia. And what it's doing is co-optimizing generation costs and reserve costs. So this is the generator costs, the quadratic. And then the reserve costs, R up and R down, are the reserve capacities in the system. This constraint bounds the power flows and is basically embedding the DC power flow equations. This constraint is computing the power injections at every node in the system, where PG is the generation, R is the reserve action taken to compensate forecast error. So these are the injections after the uncertainty has materialized, not the forecasted injections. This is the wind forecast, this is the wind forecast error, and then this is the load. There's no losses because we're using DC power flow, which makes this much simpler to solve than if we had included losses. This is the constraint I showed you before that's computing the reserve actions as a function of the wind uncertainty, where this W tilde, in this case because we have two wind power plants, is defined down here. And then that's the total wind uncertainty. We have to bound the generator output, so the total generation plus the reserve action has to be between the limits of the generator outputs. We're also bounding the reserve capacity, so this is that real-time reserve action which has to exist between two limits, and the limits are the reserve capacity and reserving, which are then lead to a cost in the objective function. So the more I reserve in capacity, the higher cost it is to operate the system. This is normalizing that participation factor to ensure we fully compensate wind error. This one is basically a power balance equation for the forecast. So the forecasted wind, to make sure that the generation meets the forecast for the system and that all additional deviations are compensating the wind forecast error. And this is just making sure all these things are positive. So that's the formulation that a lot of people have proposed several people have proposed in the past. And these constraints become the chance constraints. So these constraints have uncertainty. The power injections are uncertain because when you're doing the planning problem, you don't know what the reserve action is going to be because it's dependent on the wind forecast error. And you also don't know this here. So this is uncertain. This is uncertain because, again, of the reserve action, and then this is also uncertain. So we reformulate these three constraints, which are actually sets of constraints because these are all vectors, and stick them in this sort of form and say that these constraints have to hold with a probability of at least 1 minus epsilon. Where you choose epsilon, it's your violation probability. So in a powerful problem, you probably want to ensure that you have solvability in most of the cases, close to 100%. And this is one of the main criticisms of this type of work in chance constraint optimal power flow, because most people want this to be that these always hold, which becomes then a robust optimization problem. But in reality, you often can't achieve robustness because the problem becomes unfeasible. So they use things like 99%, 95%, and so forth. And this doesn't model corrective control action. So if this isn't solvable, it might be okay because you have additional actions you can take in the system to fix it that aren't modeled in this problem, right? So you choose that epsilon based on how much corrective control you have. So incorporating stochastic reserves into this problem means that in addition to having generators provide reserves, you also have load aggregations providing reserves. And so in this paper, we formulated a single period problem, where we define some new decision variables. So in addition to setting the generator set points, we assume some of the load is flexible, and we set the set points of the flexible load as well. So basically the consumption levels of the flexible load. And then we also determine the flexible load reserve capacities and their own participation factors. So now they're contributing to the total wind forecast error compensation strategy. We also modify the constraints. So the load-based reserve actions affect the power injections in the system and then the power flows, and those still need to be bounded properly. And then we add the constraints associated with these battery models. So basically we have to bound the actions of the flexible loads to make sure that we don't go beyond the power and energy capacity limits that I defined previously. In a single period problem, you don't actually have to worry about the energy capacity limits because energy evolves over time, right? So this is a case where you can imagine an aggregator in each hour would say, this is what I have, and the next hour they say, this is what I have based on where I am after the last hour, okay? So they're not doing planning over multiple periods, which is not necessarily great for them because they might be completely depleted in a certain hour, right? So every hour they're saying, this is how much I can change power for the system. So basically it involves implementing this additional constraint that says the load set point you choose plus the reserve action of the load has to be bounded between the maximum power capacity and the minimum power capacity, where those capacities and the baseline load are all uncertain. And what we did is we extended this in this other paper where we were looking at a multi-period case because we thought that that would be more realistic so that we could embed the energy capacity constraints, because in reality load aggregators would like to plan over multiple periods. So they didn't have to just be myopic and look in every period individually, but they could plan over multiple ones to extract the most from the markets. And so it adds the energy capacity constraints. And we look at a case where the reserves are provided by aggregations of thermostatically controlled loads like air conditioners or heat pumps or electric space heaters, where we assume all of these uncertain things, their power capacity, energy capacity, and their power consumption are functions of outdoor temperature. But the outdoor temperature is uncertain because you don't know in advance exactly what the outdoor temperature during the planning horizon will be. So we model wind forecast error and temperature forecast error. And the hardest part of incorporating all this, in addition to the constraints blowing up because you're looking over multiple periods, we solve a 24-hour problem, is designing reserves, strategies that mitigate uncertainty propagation in the system. Because you can imagine if you're planning and you're not dealing with that uncertainty continuously, it's just going to propagate in such a way that by the end of the problem, you're not going to have any feasible solutions at all. Okay, so uncertainty propagation, the issue is that the uncertainty propagates in this, basically the state of charge of these aggregations of loads. Okay, so at some point you start losing track of where the loads they are in their state of charge because their state of charge is a function of the real-time reserve actions they're taking, which you don't know in advance. And so you have to plan for almost the worst case here in a probabilistic sense. And so because you don't know where they could be in their state of charge, they could be almost anywhere, and by the end of the problem there's no, but when I say end of the problem, I mean by the later time periods there's no feasible solution. So you have to design reserves to continuously fix any deviations in state of charge. And that's what we did here. And so if you look up these papers, you'll see most of the paper is about defining these reserves in such a way that uncertainty doesn't propagate unmitigated so that you still have feasible solutions to the problem. And again, we assume you could have wind power forecast error and baseline power forecast error, which results from temperature forecast error. So if you get the temperature forecasts wrong, you don't know how much baseline power consumption these loads have. So there might be some error here. And we assume, so this is, imagine this T1 to T2 is 1 hour. And we split the hour up into 4 segments. And then we define reserve actions over each 15-minute segment. So in the first, so when there's a wind power forecast error, we have these reserves come online from the loads and the generators to compensate wind power forecast error that might arise. But then after that first segment of time, so that's secondary, that's called secondary reserves in this paper. It's basically equivalent to like automatic generation control. It's the balancing reserves you think where they're tracking a signal very quickly. After this period of time, there's a deviation in the state of charge of the aggregations of loads. And you have to compensate for it and basically drive it back to the forecasted state of charge so that you can start afresh and you know where you are in the state of charge space. And so we do that by designing this additional mechanism called redispatch, where it's the generators are essentially being redispatched every 15 minutes to fix the state of charge and other issues that accumulate because of the wind power forecaster and the baseline power forecaster. So you have the initial response by secondary reserves, automatic generation control, to fix things. But then you have this sort of error propagating in the state of charge signal, so you have to fix that again to get back to the forecasted state of charge so that you can then use the full capacity that you expect to have in the next time. And so the best way to think about this is if you had a secondary reserves market, like automatic generation control, frequency regulation is what we call it, and then you have a 5-minute real-time energy market or 15-minute real-time energy market to continuously be correcting the state of charge of any storage type device, including a load aggregation. And this might sound crazy, but California already does something like this, yeah?
Are you going to talk about how you show that this redispatch always stays feasible?
So I'm not going to talk exactly about that, but we do find that this redispatch ensures that we can bring the state of charge back to the base point within the hour or the next 15-minute interval of the next hour. And then, therefore, we don't get so much uncertainty propagation that this becomes infeasible for normal type of cases. We can find cases where it still causes the problem. But the constraints are defined in such a way that sort of in the worst case, like the frequency control actions are sort of as extreme as they could be in that period based on the bid that you offered for the reserve capacities, that you should be able to find a feasible solution because the mechanism will correct the deviations. It also means that this redispatch reserve, we're calling it a reserve, but like I said, it could be through the market. The redispatch capacity has to be quite large to fix any errors that are coming before. So redispatch has to be relatively cheap, or else it won't be economic to do this. But we assume redispatch is like a slower generation action where the generator could slowly ramp between set points to kind of smooth out the deviations. And again, this isn't so crazy because California has this thing called regulation energy management, and the idea is that they use the 5-minute energy market, the real-time energy market, to fix the state of charge of what they call non-generating resources, which are storage and load aggregations, so that you can restore their state of charge back to the forecasted one, so that they can continuously have capacity to provide both upward and downward regulation. So this is somewhat modeling that type of effect. And so in the optimization problem, we're simultaneously determining the capacities for secondary reserves from loads and generators, and redispatch reserves from the generators alone. What am I doing? Okay, so temperature forecast error causes a lot of problems in these sorts of systems. So I'm showing you two different cases for temperature forecast. So the solid line up here is the temperature forecast. Here's one case, here's two cases. The light gray in the background is the deviation of the forecast in the worst case. So you could also probably assume, in reality, maybe this would blow up even further by the end of the day. My forecast would be much, much worse. And this is the data we're using where it doesn't get too bad by the end of the day. Okay, so this plot here is showing you the baseline power consumption. That's the solid line. And then the possible deviation from the baseline power consumption in the worst case. So that's how far off we could be in the baseline power consumption based on this temperature forecast error. This is showing the same thing for a more extreme, for hotter temperatures. And then the capacities are computed again for heat pumps. And so if you have hotter temperatures, you have fewer heat pumps or electric space heaters connected to the system. And so you might have less capacity for your system. The dashed line, which is hard to see up here, but is easier to see here, is the worst case power capacity. And then the solid line is the expected power capacity. So in the worst case, you can see here that you can only actuate the system between this point and this point, the dip in that line. But in the expected case, you have much, much more flexibility. Okay, so you have to take into account the fact that in reality, you might not be at this expected case. And then these are the energy constraints. And this is basically showing how the energy constraints get tighter and tighter and tighter as you redispatch the system less and less and less. So you can imagine that if you're fixing the state of charge every 5 minutes, then you can be constantly fixing all the forecast error that you're accumulating over the system. But if you're fixing it every hour, then a lot of error can accumulate over time, and you don't know where you are in your state of charge as well. So the way to interpret this is dispatching every, I think it's 15 minutes versus every 5 minutes. It constricts and constricts. So the lightest color line is the range of energy capacity for the case when you're redispatching every 5 minutes versus the bigger ones. Every constriction means every 15 minutes, and the bigger ones are for every 5. You get a lot more room to play if you're redispatching your system more often to fix forecast error. And so we explored different solutions of tackling this problem. So initially we used what we call conventional approaches. I'm not sure exactly if they're conventional or not, but this approach was being used quite a bit when we were writing this paper. Probabilistically robust optimization that was developed at ETH, which is a hybrid approach, which is sort of hybrid between robust optimization and what's called the scenario approach for chance-constrained programming. So the scenario approach is basically making sure that all the constraints hold for a large number of scenario instances, so the uncertainties. So you draw lots of empirical scenarios, and then you ensure that the constraints hold for each of those. And the number you need to draw is a function of the dimension of the uncertainty and the decision variable vector. So this approach, the hard part with that is that you might have cases where you have, I don't know, 1 million samples that you would need to generate, and you can't solve the problem because it's just too big computationally. And so this robust version of it takes the robust set of points from that initial point. So instead of solving it for all of those points, you take the worst case of those points and create sort of like a hyperbox and then solve it for that. So that's what we did because it was computable instead of this one, which we actually found we couldn't compute for this large-scale problem. And it ends up boiling down to a quadratic programming problem with lots and lots of constraints. And we also did the more standard way of solving this type of problem, which is to assume an uncertainty distribution and then reformulate the problem. And if you assume an uncertainty distribution like a multivariate normal uncertainty distributions, you can reformulate the problem in a very nice way, and these results have been around for a long time. It ends up being a nonlinear convex optimization problem, and we've explored a variety of different ways to solve it, including just sticking it into just a brute force nonlinear solver. And then using different types of approximations, which ended up with a second-order cone programming problem. And so you can see here a comparison. So we did this on the 30-bus network, IEEE 30-bus network. And here we're assuming that those constraints have to hold with a 99% probability. And you can see here, we implemented a couple different ways, which is why you'll see multiple cases. So this is that scenario-based robust approach. And then this is the analytical reformulation, assuming that everything's Gaussian. And you can see the cost of solving the problem in the scenario-based approach is very high, and then the Gaussian approach is much, much lower. Because here you're just basically saying, we know that the uncertainty is Gaussian, whereas in reality it's probably not. The scenarios are going to capture more types of distributions that might actually exist. And you can see here, based on the solution approach, the system chooses a different amount of reserves. So GS is the secondary reserves, or these automatic generation control reserves from the generators. LS is from the loads, and GD is that dispatch. So you have to redispatch, allocate a lot of redispatch reserves to compensate for the errors that are sort of propagating from the loads, the load state of charge evolving over time. And you can see in the comparison cases that this approach procures a lot less reserves than this one, which is inherently robust. And so then you could ask, well, how robust? So this is showing you for these different approaches, what's the empirical reliability of the constraints holding jointly or individually? So what we want them to hold as is jointly. So all together they hold with a certain probability. But in reality, these analytical type approaches, usually there's not a lot of good results for the general cases where you can have constraints hold jointly. So instead you redefine them all as individual chance constraints. So every constraint becomes its own that has to hold at a certain probability level. So it's not really solving exactly the same problem because the scenario approach is for the joint case. But you can see the scenario approach is incredibly conservative. I wanted a 90% probability of violation, and I got a 99.66 in this case. And here the analytical one doesn't even meet what I set it to because the actual distribution is not Gaussian. And you can see here for the 99% case, it's almost robust for the scenario approach, and I'm not reaching 99% for the analytical one. Okay, so we know these, making these assumptions about normal distributions isn't super accurate for this problem from this result. So what we then decided to do is look at this distributionally robust optimization. I will admit that I have a grad student who became very fascinated with this topic. And we didn't pick it necessarily because it was the best tool for this, but because he wanted to dive into it, and I thought it would be fun to explore it and see if it would work well. So I'm going to show you later that maybe it's not the best tool, but we can learn something from it. So distributionally robust constraints are defined like this, where you have the probability of the constraints holding, again, 1 minus epsilon But the chance constraints are satisfied for all distributions within a data-driven ambiguity set, which is this script D. So we're defining distributionally robust constraints the same way that Delage and Yi do in this paper. So basically, you want all those constraints to hold for uncertainty distributions that exist within a set, and you define that set. So maybe you take a bunch of data from your system and use that data to compute the mean and the covariance or other higher order moments. And you want to say that all distributions with that mean and covariance and whatever else should be satisfied by so the constraints should be satisfied for those distributions that exist in that set that you're choosing. So people have looked at this in terms of moment-based information that you gather from data, density-based information, and structure. So you could know the support, you could assume that the distribution is unimodal, symmetric, et cetera. And there's been a lot of very recent papers on distributionally robust optimal power flow. It's there's conferences where there's whole sessions on this right now because everyone's excited to explore this idea. Because in reality, we don't have good estimates of these distributions, and these scenario-based approaches or fully robust approaches are just too conservative. You wouldn't want to implement them. So this seems like a good compromise. So in this paper that I mentioned before, we use this ambiguity set here, which is basically this is basically just normalizing the PDF to 1, and then this is saying that the mean and the covariance exist within a small space of the empirical one. So if you measure the empirical one, you know that the empirical mean or covariance isn't exactly what it will be in real life because you're not using an infinite number of samples, but you should be kind of like in a ball around that. And that's what this one is saying, that you use the empirical data to calculate these things, and then you need to be close to it. And you can reformulate a chance constraint OPF with this ambiguity set, and it ends up being a semi-definite program. And we also tested another ambiguity set that's less computationally intensive to solve, where we basically, instead of being in a ball around the empirical value, you just match it. You say, this is the mean, I want to be at that mean, or this is the covariance, I want to be at that covariance. So it's less conservative, but perhaps less accurate, less reliable. So that's a second order cone program. It's much more scalable to solve. There's too many numbers on that, but if you focus on just what I'm showing you here, this is again that Gaussian approach. This is that robust scenario-based approach I told you about before. And then these are the two distributionally robust approaches. This is that first one with a semi-definite program, and then this is the second one with a second order cone program. This is showing you the cost of solving the problem, reliability, and the time associated with solving it for the 9-bus system. 9-bus system is not very compelling. We've tested this on the 118-bus system. I'll tell you about that in a second. But basically what this is showing in this case is that we know that the scenario-based robust approach is already very conservative. And you can see that actually our distributionally robust case is even more costly. So it's not a good compromise in this case. And, oops, whoa, I apologize. And the reliabilities here that we're seeing are way above the requirement for the scenario-based approach, but also for the distributionally robust approaches. It's too conservative. And so far it hasn't been a good compromise. So then we tested it on the 39-bus system. And again, this is the same order, the Gaussian approach, scenario approach, and the two distributionally robust. The main difference is here we tested two different reliability levels, and here we just are using 95%. And you can see in this case, the distributionally robust approaches are a compromise between the scenario approach and the Gaussian approach. Okay, so they're cheaper. I think, yeah, they're cheaper, so that's good. But then we start to see issues here. So in this second order cone approach, the reliability is still higher than we need, much higher than we need. But in this semi-definite programming approach, it's very, very low. And actually, this one should be worse, well, more conservative and higher reliability than this one. And so we're actually starting to see issues with our SDP solver because the problem is becoming too big already. And so it's not converging to the optimal solution, so it's not going to scale to a realistic system. So we got to this point, and then we tested it on a 118-bus system. We couldn't even make it work for the STP version. We got the SOCP working, and it was a good compromise between the scenario approach and the Gaussian approach. So there's still a lot to do here to figure out how to make these reformulations scalable. So some thoughts, taking a step back. is this worth it? We're throwing a lot of math at this problem that the system operator admittedly will never use directly, but can we find these kind of compromise solutions that get closer to what we want to achieve in terms of reliability? We don't need to be as robust as we are. That will really reduce the system cost. And it's not clear with the existing tools from this space that we have the answer yet, if this is the right thing. So what we naturally ask then, of course, with the graduate student who is super excited about distributionally robust optimization is, can we improve the theory? And so can we be less conservative while sufficiently reliable and ensure that our algorithms are scalable to large networks? So we don't have to use semi-definite programming, for instance, or, I think those solvers are improving quite a bit. This isn't really my area, but some people tell me that I shouldn't worry about that long term. So making it less conservative, I'm running out of time, so I'm just going to tell you the highlights here. So the first thing we said was, well, if we're defining an ambiguity set based on the moment, so we're matching the mean and the covariance of the empirical distribution, we're considering these really wacky distributions, like bimodal distributions with lots of density faraway points, when we know that these distributions of forecast error, especially for something like wind forecast error, are actually quite nicely behaved. So my student went and got wind forecast error data and plotted it and said, well, that's clearly unimodal. And I think it's a pretty good assumption that these errors are unimodal, but the ambiguity sets that we're using in distributionally robust optimization weren't incorporating this level of information. So it could have considered bimodal or trimodal or whatever distributions that are totally unrealistic. So then you have to be robust to that too when you don't actually care about being robust to that. So this is just visualizing with real data from Europe what these distributions look like for one wind plant or for two. And they generally seem fine to assume unimodality. So we derived a new ambiguity set here where we're matching the mean, the covariance of the empirical data, and then we're assuming unimodality. This type of unimodality called alpha unimodality, which is defined in this paper. This paper, which we published in Mathematical Programming, we derive exact and approximate reformulations of distributionally robust chance constraints. We also looked at C-bar constraints, and we came up with some efficient solution algorithms to solve the problem. And we solved it for the simpler version of the optimal power flow problem I showed you before. We're not considering stochastic reserves here, just wind forecast uncertainty. But what this is basically showing you is for the original case where you don't assume unimodality, that's this black line. With C-bar constraints is the red one, chance constraints is the blue one. The optimal cost of operating the system as a function of the distance between the mean and the mode. So the mode is at 0, and the mean varies based on where you are, lower or higher than. So if your mean and mode are at the same location, these solving the problem assuming unimodality doesn't help you quite as much as it does if the mean and the mode are far apart from each other, and then including unimodality information really helps reduce the cost and conservatism of the system. So in this case, we're solving the same problem for a lot less cost, and it's sufficiently reliable at the level that we set it to. Okay, so adding more information with reliable information that you can trust is certainly going to help you reduce conservatism while maintaining reliability. It's just that there's this issue of, can you add that information without making the problem computationally intractable and provide guarantees? In some cases, like in this case, we added information and we can't exactly reformulate the problem. So here we said, imagine the distribution is log concave and the support is ellipsoidal. We haven't figured out how to reformulate that problem exactly, but we've come up with a sandwich approximation, so we've bounded the solution based on a conservative and a relaxed approximation. So in this case, the total cost of operating the system is shown as a function of the confidence level. So usually we're operating the system way up here, where the confidence level is close to 100%. The benchmark case is without log concavity, and then the conservative approximation and the relaxed approximation show that the real solution exists between the yellow and the red. So it's kind of tight approximation, not bad. And then the Gaussian approach is way down here just to show that it's bad. Where its cost is low, and actually it doesn't show that it's bad in this plot, but it's bad in the sense that the reliability isn't sufficient. But what we found here is that as you get to really high confidence levels, which is where you would need to be, these approximations approach the benchmark, so why not just use the benchmark, which doesn't make the assumption of log concavity. So again, in some cases, like based on what you need to how you need to set up your problem, even if you define this ambiguity set very precisely, it might not give you a significantly better solution just because you basically have to be so robust anyway to meet the power system requirements. And then lastly, the thing that we've just been working on is going back to the work on unimodality, not log concavity, but assuming in that work you assume you know the mode of the system. But in reality, you have to estimate the mode based on samples. And mode estimation is much harder than mean estimation. It depends a lot on how many samples you have and how you bin the samples. So basically, you usually create some kind of histogram, and you see which point in the histogram is the highest. But how you choose the discretization of your histogram will affect your perceived mode for your system. So what we did here was we took a bunch of data samples, and we used the samples from the same uncertainty set to generate the mode and the mean. And you can see this is for wind forecast error from one wind plant and then from another plant. The means are nicely clustered. It's not perfect, but the means are pretty robust to sampling error. The modes are all over the place. And then this plot is showing the difference between the mode and the mean to show how much issue you get in knowing how far apart they are. And you can see the origin is where the mode and the mean are the same, and you get a lot of variation here. Okay, so this means that the assumption we may be for with the unimodality application where we know the mode isn't maybe so accurate. And so what happens when we misidentify the mode? So just high level, we find that they can significantly reduce the reliability of the previously presented approach. So what we do in this paper is instead of matching the empirical mode, we confine it to a set constructed with historical data. So we generate a bunch of mode estimates, and we say the mode's in this set. And then we redefine the ambiguity set, saying the mode has to be in a set instead of at a point, and then resolve the problem. So it makes it more conservative because we're allowing the mode to vary, which increases the cost. But when the mode is misspecified, it works, and you can get reliabilities at the required level, whereas with the original approach, it doesn't. So we're kind of digging into all these different areas to see what matters. But inherently, we're dealing with creating information and an understanding about uncertainty distributions using real data that's fundamentally limited and inaccurate and varying across continents and across states and across geographic regions. And so these sorts of issues associated with data quality, having sufficient data, et cetera, are going to be a problem. And so the methods have to handle that. Okay, so lastly, concluding remarks. So I hope I've convinced you of this first one. Load aggregations can provide reserves. I think that's not controversial, but their capacities are uncertain. You can plan for the uncertainty, and you can have the aggregator do that or the system operator do that. It's not clear who should do that or if a hybrid of them should do that. I think it's interesting looking from the system operator's perspective because we can understand sort of a best case scenario for the system. But I think in reality, the system operator wouldn't want to take on the full burden of doing that. And this idea of using distributionally robust optimization might have promise. It might be a good compromise between assuming you know the distribution versus solving something that's almost a robust optimization problem. But it's still not clear based on our results if you get the right trade-off in terms of cost and reliability. It's too conservative in our cases. And it's also not clear if we're going to get to a point where we can define the problem such that you have reasonable computation requirements to scale up to systems. The largest system I talked about here was 118 buses, right? We haven't gone to the 1,000 bus systems that you would need to solve on to make this work in real life. But again, I do not think that system operators would use this explicitly. We can use this to inform insights that they can use to modify how they do the dispatch to get closer to optimal. So that's all I have. Thank you.
Like a formulation, but why don't you solve it all end-to-end and basically allow the aggregator to submit a supply function which will specify the quantity as a function of wholesale price in the day-ahead market?
So if they could supply that in addition to some notion of the uncertainty that they have about their capacity, then that would be similar.
Yeah,
but they don't know their supply function.
Optimize that simultaneously with everything else, where you would basically, the quantity would be a function of the wholesale price, and then you have some sort of, if you don't meet your obligation, you pay their real-time price as a penalty.
Right, so their supply function is uncertain in this case.
What?
And so their supply function is uncertain because they don't know their capacities in advance. They only have a guess for them, as opposed to generators, which would know. And so because it's uncertain, I'm suggesting that they basically send that information plus the uncertainty associated with it, so that the system operator can figure out how to best utilize it, given that it's uncertain. But what you're saying is kind of the other approach where the load aggregator internalizes the uncertainty.
One more, because California actually has a tariff for aggregators where the aggregators can put together resources,
Sure.
like you described, and submit a supply function.
Right.
For the quantity.
Yeah, but the aggregators have to be careful that they don't commit too much because of their uncertainty.
Like a reverse
So they're
problem.
figuring out how much to sort of downscale based on their expected value, and they're dealing with it. So I think that's one option, but I think that it's also interesting to look at the case where they let the system operator manage the uncertainty collectively with the uncertainty of the entire system to see if you can use more of these types of reserves.
Well, the system operator ends up optimizing the supply function that they get from all,
Yeah, sure.
from all the aggregators or from all the resources.
Yes.
So what you want is an aggregator that basically behaves like a virtual generator and submits a supply function. So your aggregator should behave like a virtual generator.
I think that's how it would work.
Longer
Yeah, sure.
discussion,
Yeah.
and
Go for
so
it.
maybe we can have that discussion
Sure.
offline and have one additional quick question, because there were a lot of questions.
Yeah, yeah,
and I
sure.
want to give other people time.
So, in your formulation, what is the ultimate goal? You want the renewable renewable over time minus consumption to be less than equal to epsilon for all the time, or do you want renewable generation minus consumption to have certain slope, or what's the ultimate goal for the demand response of like moving the loads around?
At every time period, we want supply and demand to be balanced.
Do
And
you
so-
want all the thermostatically controlled loads to be served only by renewable generation and by nothing else?
No. We want to make sure that there's some load forecast, there's some wind forecast, and then we schedule the generation to meet that, right? In real time, the load forecast and the wind forecast are going to be inaccurate.
Right.
So we want the generators and the controllable loads to change from their nominal values to increase or decrease to balance that forecast error.
Sure. So you consider the ramping constraints of the generator in this, or generators
could.
can go up and down?
You could, yeah. I mean, I didn't explicitly model that,
Oh,
but
you didn't. But,
no.
but that's something that you would. That is a realistic constraint for a generator, right?
you could add that, exactly. I mean, we're assuming that the generators that are providing frequency regulation can respond very, very quickly, but that their frequency regulation is inherently expensive and also could be bad for the environment because they're ramping up and down.
Sure.
So can loads provide that instead?
Of course,
Yeah.
At the back with your question really quick.
Basically there is a weak relationship between the variable capacity of the aggregation of loads that you showed and the amount of reserves required. So if I see in a longer horizon, the amount of reserve required would be kind of independent of all of my aggregate loads, because I have to design or deploy my reserves based on the worst case scenario. So how does load aggregation helps in this case?
I don't understand.
So my question is like the load, the capacity that you showed for the aggregated load is variable over time.
Yes.
And that has a weak relationship between the amount of reserves required at any point of time. So if I'm looking at like a longer time horizon, then the amount of reserves that I have to deploy, have to plan, would be the worst case scenario, which will be.
We redeploy the loads like at every time period. So like every hour you can deploy a different amount of reserves. So you're not restricted to only deploy the smallest amount that I showed on that plot that increased and decreased at night. So the reserve capacities are changing throughout the day and every time period. I don't know if that's answering your question.
Maybe you can discuss later.
Sure.
All right, I think we only have an hour for lunch, so we'll cut off the questions here, and hopefully Johanna can answer some more during the break.
Okay.
Thank you very much.
Thanks.